Welcome to MEI Numerical Methods Convergence. In this video we'll be looking at numerical integration. Now if we're using either the midpoint or the trapezium rules to find an estimate for an integral which has true value alpha, and if we're producing a sequence of estimates, say for the midpoint rule, where we're doubling the number of strips each time, then it can be shown that the absolute error at each stage, which is mn minus alpha, is approximately proportional to the square of the width of each strip, i.e. h squared. And for this reason, because it's h squared, both the midpoint and the trapezium rules are described as second order methods. Now this is not to be confused with when we talk about second order convergence, which we'll be clarifying in a second. So we've got the absolute error for mn here. So if it's approximately proportional to h squared, we can write it in the form k h squared, where k is a constant. And then if we double the number of strips to get to m2n, then we're going to be halving the width of each strip. And so if we take the ratio of m2n to mn, then we've got k h over 2 squared divided by k h squared. So the k and the h squared are going to cancel, and we're going to be left with a quarter. So rearranging that, we see that the absolute error at the 2n stage is a quarter of the absolute error at the previous n stage, and of course that means that we've got first order convergence as opposed to a second order method. And we can work out the ratio of differences just as we did for the solution of equations example. So we've now got, as already mentioned, we've got this sequence m1, m2, m4. So it's very important to note that it doesn't go m1, m2, m3. We're doubling the number of strips at each stage. So we can find out the ratio of differences, and if we did this in a spreadsheet, we could see that it would settle down to it should settle down to a quarter. And then we will get the same thing for the trapezium rule. Now we've seen that Simpson's rule gives us much quicker convergence than for either the midpoint or the trapezium rules, and it can be shown that in this case the absolute error is approximately proportional to h to the 4. So that makes Simpson's rule a fourth order method. And if we investigate the ratio of the error terms as before, then we can see that S4n, or the absolute error in S4n, because we're doubling the number of strips, that's going to give us k times h over 2 to the power of 4, and then dividing that by the absolute error for S2n. And as before, the k cancels and the h to the 4 cancels, leaving us with 1 over 2 to the power of 4, i.e. 1 over 16. And we can use the ratio of differences as before, and we would expect that to be approximately 0.0625. So Simpson's rule is a fourth order method, but because each absolute error is approximately a certain proportion of the previous absolute error, that makes it first order convergence again. So that concludes this video, and we'll be looking at numerical integration further in the next video.